Streams Interactive Queries. Bill, take it away.
Thank you, Donica. Just to set the record straight, if y'all are expecting me to play an instrument, feel free to leave now, because that's not going to happen. Okay. So this is real quickly about me. The most important thing on this slide is the second edition of Kafka Streams and Actions coming out, and by attending, you're required to buy like 5 copies. All right, so our agenda today, we're going to do a background on Kafka Streams. Then we're going to give a quick background on interactive queries. Then we're going to talk about internal communication between Kafka Stream instances. Then we're going to talk about custom queries, and then we're going to wrap it up covering some performance considerations. All right, so Kafka Streams is the native stream processing library for Kafka. What you see here is a Kafka Streams application that you've written. This is using the DSL. There's also a processor API that I'm not going to cover today. But you use this Fluent interface pattern and you build up, this is a streaming application, and this is doing a stateful aggregation. Now under the covers, what that DSL is doing as you write that, when you run it, it creates what's called a processor topology. And that is a connected, a DAG, a directed acyclic graph. And each statement in your DSL creates a processing node. And you have a source node and then the processing nodes and the sink node. And what I want to call to your attention here is the aggregation creates a stateful processor, and there's a state store attached to this. And this is, by default, it's persistent and its own local disk. It's RocksDB is the implementation. Now, we need tasks. We've got this topology, but we need a unit of work to make this, to drive this. In Kafka Streams, the lowest unit of work is a task. And you get a task from, the number of tasks are determined by the input partitions of your source topic. So here we're going to say we've got 4 input partitions, which would give us 4 tasks. Each task is going to have its own copy of the topology. And it has its own copy of the topology, and it's going to have its own state store. So you get a state store per partition. And what's important here is that this is a shared nothing architecture. Each task only works on the data from its partition. So each state store just like works in isolation. The task works on that in isolation. They don't communicate with each other at all. And then when it's done processing, you may be writing out to a sync topic. So we have the task, but we need execution for this to actually run. In Kafka Streams, it's a stream thread. And you can have up to as many stream threads as you have tasks. If you have more, that's fine, but they're going to be idle. And so what we have here is 4 stream threads. But instead of thinking of this as a single host with 4 threads, think of this as 4 individual hosts, each running a Kafka Streams application with 1 thread. So right away, since you get a state store per partition, your data is sharded across 4 instances. And we'll see why this is really important coming up. So now we're going to talk about interactive queries. To give you some context, let's just say you've got your stateful application, you want to expose that because you're doing an aggregation. So the only reason you're doing that is you want to see the results of that. You're trying to determine something. So you would write the result out to a topic, then maybe use a sync connector, and then you maybe play the cello, but you have a sync connector and you export it to a database. And then you've got, say, a web application, and the web page is making REST calls to a web server, which is going to turn around and hit the database to show the results. What interactive queries does is it gives you the opportunity to possibly simplify your architecture, is you can directly query those state stores. So now you're going to send your REST request to the web server, which is going to turn around and query the state store. Now, I had said before that your state is distributed, and the state stores are key value pairs. So what that tells us, if you've got distributed state, you send a request for a given key, there's a chance the instance you hit is not responsible for the partition where that key is going to live. So what Kafka Stream does is it provides the metadata that each instance, you don't have to worry about which one you're going to query. You send your query, it has metadata that's exchanged during a rebalance. It can determine which instance is responsible for that key. And then it can issue the query on your behalf, get the result, and return it to you. So what we're going to talk about today is Kafka Streams provides the metadata and the plumbing to determine the different members of, when you have a Kafka Streams application and you have them deployed on multiple hosts, it's considered one logical application. All the ones that have the same application ID, it's considered one application. So they all are aware of each other and know which one is responsible for which partitions. But you have to provide the serving layer for handling the request from, say, a web server and the internal communication. Now, to enable interactive queries, you have to explicitly name your state store. If you don't name it, Kafka Streams gives it a name, but it's just a one-up number with, I think, like state store appended to it, and it won't be available for querying, so you have to give it a name. And the next thing you need to do is you have to configure the application, you have to set the application server configuration. And what this is the host and port that's going to accept the request for querying. Now, for executing the query, it's a two-step process. First, you determine the correct host, and I'll talk about why I have that asterisk there in a second. And then you need to query the current instance or forward it to the correct one. And that's all it is. And then for metadata, you have this query metadata for key method, which gives you back the metadata you need to determine. And that's just a process of, am I on the correct host? Is this the host that has it? If it is, fine, do the query. If not, you do the remote part. And then the actual execution of the query, you use the Kafka Streams query method. Now, specifically today, I'm talking about interactive queries version 2. There's a version 1 where you would actually just retrieve a read-only version of the state store and then do the lookup yourself. With interactive queries version 2, we now have this query method where you pass in a request, the store name, and you have a query object that you give it. And we've got 4 types. You gotta have a key query, a range query, and then windowed versions of those. Now the range query variants, I have an asterisk there because Kafka Streams by default does hash partitioning. So you're doing a range, you want to get all the records between key, your lower bound is A, your upper bound is F. You want the full range. But since it's hash partitioning, we can determine, okay, A is on this host and the lower bound F is on this host, but everything in between we don't know because it's hash partitioning. So we have to, when you have a range query, you have to issue it to if you have this deployed over you have 3 Kafka Streams instances, you have to issue that range query to each one, gather all the results, and then you have your final result there. So that's why range queries are a little different. So now let's talk about building the query service. To do this, we're going to build a web application, but we're going to have several components that we need to use to do that. You have the web application itself. We're going to have a REST controller that's going to handle the incoming requests. And then we need the Kafka Streams instance we need references to that to actually do the query. So to tie all these components together, we're going to use Spring, specifically Spring Boot. Is everybody here familiar with Spring? Okay. For those that aren't, Spring is a inversion of control container, which just basically says the application doesn't know where it's getting dependencies from. They just get injected into it. And Spring is going to handle that wiring up for us. And Spring Boot embeds a web server, and it allows us to quickly stand up a web-based application without a whole lot of fuss. Now, I will say Spring has functionality for Kafka and Kafka Streams that I'm not going to use. And I'm pretty much a purist. I think that you just want to use native Kafka Streams. Using some of the annotations that are provided, it does a little bit too much for you. So I prefer just to use, like I said, native Kafka Streams. So how this is going to work, you would create a wrapper class, and then you give it the component annotation, which just tells when it starts up, Spring is going to scan the class path, find anything that has a component in it, and then start doing its wiring together of things. any dependence, any other class that has a dependency on Kafka Streams, Spring is going to execute this method to inject the Kafka Streams instance into it. Then we'll also use Spring for controlling lifecycle. Anything with this post-construct annotation, after it instantiates the class, it'll execute this method. So this will create our topology, create the Kafka Streams object, and start it up for us. And the reverse is true. You're shutting down. As it's shutting down, Spring will execute this method to close our Kafka Streams instance. Now for handling the REST call, we're going to have this controller. REST controller does some nice things for us. One of them is it'll automatically serialize our objects going back to the web application in JSON. And this is the base path. So anything starting with Streams IQ is going to go to this controller. And then when you have this at the end, these are the individual methods that'll handle your different requests. And then we have our lower and upper bound and a predicate, which we'll get into more a little bit later. And these are all optional parameters. Okay, so now we want to talk about the internal communication. I had said before that you've got this web page, makes a REST call for a given key. And let's see, the one you hit, the instance you hit, it is responsible for it. You just return that. But if it's not, we need to, that instance you queried will know which one to hit. But now we need to, how do we communicate to the other instance that we want to issue this query? So how are we going to handle that? Previous versions of this, I just reused the REST API, just turn around and make the same REST call. That worked for key queries, okay. But with range queries, it presented a problem because with range queries, I mentioned before, you have to query every instance. So if you've got 3 shards, you have to query each one. So it ended up in this infinite loop because each instance would accept the request and then turn around and then determine who the other members were and then just start issuing queries. So it was just this giant infinite loop. So what I determined is it's really best to have an external API and an internal one, because you want to handle when one Kafka Streams instance is querying another, you would treat it differently than if it's coming from an external client. So I determined that the best way to do this is we're going to use Enterprise Java Beans for internal communication. Okay, that's a joke, folks. And if you don't know what EJBs are, consider yourself lucky. I saw the face of my colleagues up there, and they were just like, "Oh, what?" No, we're going to use GRCP for internal communication. Why use GRCP? It's a high-performance RPC framework. It's quick to get going. You just add some service definitions to your proto file, and it uses protocol buffers for serialization, and it's more performant than REST. I've got an asterisk here. With GRCP, it's optimal to reuse the connection. I didn't do that in this implementation, so the performance benefit might not be as much. It's got great integration with Spring Boot, and the support, there's Gradle and Maven plugins for working with protocol buffers that make it pretty trivial. You just configure your build file, and then when you run build, it'll generate everything for you. So this is our aggregation that we've got as a proto definition. And then within the proto file, we're just going to define this service. And these are our service methods that we have. And then the plugin will generate a base class for you that you need to extend. And then just by putting this annotation at the top, Spring will handle starting up the gRPC server and then shutting it down. And then in the configuration, you also have to give it a different port number. And then once you, this is, again, we're just showing that we need to have Spring inject the Kafka Streams instance into our service implementation. And then you just, from your base class, you just override your different service methods. And these are the parameters it's going to accept. And then from there, you would just, internally here, you're just going to unpack the information from the request, do your Kafka Streams query, pack up the result, and then use a response observer to send it back. It's pretty straightforward. So now we've got our internal and external communication. So there are some trade-offs for using gRCP, RPC. First is it kind of nudges you to use protobuf throughout your Streams application. Not a big problem, but it really makes sense just to go ahead and use protobuf straight across the board. And you need to have protobuf equivalents for other classes that you're using. For example, you have host info, you need to have a protobuf equivalent of that. You could pack all this up and just set the fields in one big object, but I think that's a little messy. It's better to have just the protobuf equivalents. And then finally, protobuf is not using Jackson, the Jackson mapper object is pretty standard for serialization to JSON and from JSON to an object. Can't do that with protobuf. You have to use, there's a, Google provides a protobuf utility class. You have to use the JSON format class that will allow you to serialize protobuf to and from JSON. So you have to put this in your Spring configuration. All right, so now we're going to talk about custom queries. So why would you want to write a custom query? Let's go back to our example of using a range query. So your client sends a range query, and let's just say you've got 3 instances and you've got 12 gigs of state, and we're going to assume even key distribution. So you've got 12 gigs of state, so it's going to be separated across 3 instances, each one having 4 gigs. So you send your range query, and we need to get the full, we need to issue the range query against each instance, which means you're going to need to pull back from each other member of the group 4 gigs of data. And if you want to just get a, let's say you're looking for a specific subset of records, that means you're pulling 4 gigs from each one across the network just to do some filtering. It would be better if we could send a predicate up, and then the instance you queried would push that predicate to the other instances, kind of pushing it down to the store level for all the other instances. So you would filter on each instance and only send back the records you're interested in. Now to do this, we would need to write, the queries we have right now don't support setting something like this. Now the original intention of IQv2 was that if you wrote a custom store, custom state store, it wasn't available for querying. So IQv2 made it so that if you wrote a custom store, you could query it. So I kind of turn it on its head a little bit. I don't need the behavior of a custom store. I want to write a custom query. But I still need to take some steps to have a store that I can override the query method. So what I did was you extend the query interface and create a wrapper, a class that implements the key value store interface, but it just accepts a delegate of an actual Kafka Streams state store that it can delegate to, and then override the query method. And currently working on a proposal for being able to register a custom handler so that in the future, if you want to write a custom query, it would just register it. You wouldn't need to go through these other steps. So the first thing we do is we just create a marker interface that extends the query interface. And then you just create an abstract class that implements the key value store. All of the store implementations in Kafka Streams are in the internals package, so it's best not to directly extend those. So we've got this wrapper class, if you will, and then we pass in the delegate. And so pretty much every call, we're just going to just send it through to that underlying store, except for the query method. That's the one we want to override. So we check, we come in, and when it accepts, gets a query for looking up, we just If it's not a custom one, we just defer to the underlying store and that's it. So all the existing queries are automatically handled. But now that we get a custom query, we can handle that directly. And then we're only going to talk about the filtered range query. And the filtered range query has an upper and a lower bound, but it also takes a predicate. Now the steps we're going to take to enable this is we're going to serialize our aggregation into JSON, stored as JSON in our state store. And then we're going to use JSON path, which gives you the ability to examine a block of JSON similar to what you would do in XML with XPath. And it's got these operators. So this code you see right here, this is what you can do to look for. You've got say a JSON array, and you want to pull out the elements where it has a price field greater than or equal to 9. So what's going to happen is our client is going to send up a string that looks like this. Then this is the filter criteria, and that's our predicate. So we're going to do the range query, which if we haven't specified a lower and upper bound, we're just going to do the full range, get everything out of the store, build up a JSON array. Then using JSON path, we just apply this predicate, and it's going to give us back the only things that match this predicate. And then to plug the store into our Kafka Streams app, we're just going to you just do it normally like you would with any state store. Create your supplier. You have a custom. Also extended the stores class so it knows how to give us the correct supplier, and then just plug that into materialized. Okay, so now we're going to do a demo. It's going to start our broker. Okay, and now we're going to create some topics. There we go, input and output, great. Okay, so now we're going to create start one. Okay, and now we start application 2 running. Okay, and then now we're going to produce some data. Okay, so let's go ahead and issue just going to do this from the command line. Okay, so here we've got a bunch of results, pretty evenly distributed, and we can see that we got half from the instance we created, and we got the other half, which we'd expect from the other instance running via gRCP. So that's our internal communication. But this is a lot of data pulled back at one time. We want to, let's just say, we want to pull back the stock transactions where the amount of the buys are more than the amount of selling transaction. So that cuts it down in about half, but still it's a lot of data. We want to really drill down and get something more specific. So we're going to, we want to get the transactions where the purchases were more than the sales, but the number of shares involved in the transaction were greater than, say, 50,000. And so now we're able to pull back just a few results. And what you can see at the bottom there is only one result came from the other instance that was running. So it did the filtering and only sent back one record versus before would have sent back 100, and you would have had to filter that on that particular host. Which in this case is a small amount, but if you think about the fact if you've got multiple instances and you've got a large amount of data, then this is much more efficient. So now we're going to wrap things up by talking about performance considerations. So you're running your Streams application, and then you're accepting queries. Knowing that there's no free lunch, what's the impact to your Kafka Streams application for running interactive queries? So on my laptop, I just ran a simple benchmark. I have a key space of 200, and I produced 8,000 records per second. And then I just started up the Kafka Streams app and let it run for 10 minutes. And then the metrics that are available in Kafka Streams, the thread metrics, there is a process rate metric. And that'll show you how many records are processed per second for the tasks on that thread. So I ran that for 10 minutes, captured the process rate. And then I fired up interactive queries, let it run for 10 minutes, and then took the process rate again. And then for running interactive queries, I just used a super sophisticated load testing tool. Just ran curl in an infinite loop and just dropped the results. And this equated to about 55 requests per second, or 3,300 a minute. And what I observed was that just running Kafka Streams without accepting any interactive queries, it was processed about 7,300 records per second. Then starting up interactive queries and just letting that run, it processed about 6,700 per second. So it was a performance penalty of about 7.35%. Now there is a possibility with interactive queries that you could query standby tasks. So I didn't get into that in this talk, but if you were to enable standby tasks, you have metadata available to you to know where those standby tasks are. So you could query the standby tasks, so you probably wouldn't incur the processing penalty. But the difference with a standby task is it might not be fully caught up because it's reading from the change log. And that's what I have. So to wrap it up, interactive queries allows you to view the state of a running Kafka Streams application. You can use Spring Boot to quickly stand up a web application to wire everything up for us. And then gRCP is a good mechanism for us establishing that internal communication. And IQv2, not only can you query a custom store, you could also use it for just creating a custom query. And that's all I have for you today. Thanks.